So for calculus, did anybody tell you why you do calculus? Anybody ever tell you why you do it? It's fun, good. But here's the if anybody asks you what calculus is, this is on the street. This is what you do. You tell them.
That's what normal humans do, right? Yes.
You'd be surprised. I ask calculus teachers at colleges what calculus is, and they cannot tell you what it is. Well, we take derivatives and integrals. Okay, but why do you do it? Well, it's so we can find area and slope. Okay, but how does it all connect? Here's the best way to describe it. If you look at a graph of time versus amount, and you have a function like this, f of x, what can you find? Instantaneous rates. You can find little slopes. That's what you can find. And you find slope using what? By the way, slope is the amount per time. And what's amount per time the same as? What do we describe it? For everything, it's called a what? Yeah, it's a derivative, but it's a rate. And this is what we use the derivative for. Okay? That's one part of calculus. The second part of calculus is if you have time and you have a rate. Okay? And you have a function, f of x, what can you find with it? You can find an amount. So if you take the area of this, yeah, the area is what we find with calculus. But what we're really doing is we're taking the rate and the time, and what are you doing with it if you're finding little rectangles and adding them all up? What is rate times time? That's the amount. So the relationship of calculus is quite brilliant. You're taking a function in amount time, finding rates, or you're taking the areas under rate times to find amounts. Now here's what's helpful to you. If you're ever taking a test and they have any graphs or a problem, if you see the word rate as your y, what are you probably going to want to do? Integrate. If you see amount and time, or amount in some variable, what do you think you're going to do? Derivative. So I think that's super helpful of knowing the difference between when to use rate and when to use amount, or when to use derivatives, or when to use integrals. And this is a great intro for integrals because that's exactly what we're going to do, is we're going to find some kind of a, I like to say time, but it could be other value. And then here is going to be rate. So if we're looking at that, we're most likely doing it. Now, there are some exceptions. I think it's power for electricity is voltage. Oh, what is it? No, power isn't it. But, work is distance times what? Work. Force times distance. There you would have two quantities that don't have rates to them, force and distance, but those do find an area, gives you work. And there's some other ones too. I think isn't it voltage times current? Isn't that power? Physics people? Voltage times current. All right, so there's some exceptions, but most of the time rate is going to be here. All right, so what's the deal with this curve? How does mathematically how we do this? Well, we're going to see a really good proof of this tomorrow, and if you're gone, we'll get you back up to speed. But essentially you're doing is dividing this up into strips, and these strips are going to have y values that'll give us estimations of areas. Now, if you could make these thin enough and add an infinite number of them, you'd get a perfect answer for area. And that's essentially what we're doing with integrals. Okay? We're taking these sub-partitions, we're adding them up, and we're getting an area. And so the area is written as the integral going from low to high. So I like to say low to high And you remember that? You remember this last year? And then of the function. Now, this should not be too confusing to you. Think of a rectangle, and this is time, and this is rate. Okay? Now, any area is going to be what? Of a rectangle. Base times height. So this here is my height. What do you think dx is a representation of? The width. And by the way, thank you for not making fun of me. It's the one word I can't say. I can say aluminum, I can say cinnamon, I cannot say width. W-I-D-T-H. How many of you also have trouble with width? Thank you. Okay, good, good. So thanks for not laughing at me. I appreciate that. The width. Okay, they talk about different areas, but when you look at the integral, height, width, I don't want you to say, why do we have to have dx? Because dx is your what? Thank you. Thanks for saying it for me, too. All right, so there's some things you can read. You can add different areas. You can take opposites. That you can read about. What I want to get to is probably the most important part, the fundamental theorem of calculus. Does it sound important? Yeah, it sounds pretty important. So let me go to a blank spot. Fundamental theorem of calculus. Shouldn't be talking right now. Thank you. Okay, so for the fundamental theorem of calculus, what I want you to remember are two things. The one that you like the best is that if you're looking for the area going from a to b of little f of x function dx, by the way, what was f of x for a rectangle? What was dx? Width. So, and we're accumulating these from x's here. This will make more sense. But you essentially take the antiderivative, put a b in it, the top one, and then you subtract the antiderivative, put the bottom number in. That's the one you're most familiar with, right? For fundamental theorem of calculus. And there's some boundaries to it. But what I want you to do is just to remember that there's two things in the fundamental theorem. That's the easy one. The one that's a little tougher to remember is that if you took the derivative of the antiderivative from a constant to a variable of f of t dt, essentially what will happen is you'll get the derivative of the antiderivative of f of x minus f of a. By the way, what's the derivative of the antiderivative of f of x? It is just plain f of x. What's the derivative of a constant? 0. And so what this says is if you take the derivative of an antiderivative, they're like inverses. One undoes the other. The derivative undoes the antiderivative undoes it. But I do want to warn you that flipping these around, going from a to x of d dt of f of t dt, do you think that's going to be the same thing? Well, the first thing you do is, this is the first thing you do here, antiderivative. This is the second. When I take the derivative last, what happened to the constant? Disappeared. But what do you think happens when I do the antiderivative last? You're going to get f of x minus f of a. It's included. So it's not quite just as simple as saying f of x. It is if you take the derivative last, you're good shape. But if you take the antiderivative last, not the case. So that's fundamental theorem. Derivative, antiderivative, hand in hand, inverses kind of. And then 2 is the breakdown of that integral. Go down to, you can read about these a little bit. What your assignment for Wednesday is going to be is to go through these clues. This is like a puzzle. See if you can figure out what these areas are. And then sketch it here. Piecewise, you won't have trouble with that. These are just some basic things having to do with derivatives and antiderivatives. Fundamental theorem, we'll go over them on Wednesday.